And we should have some time today for homework or practice test questions in case anybody has them. Okay. So this course basically breaks down into three parts, because there was the first part about partial derivatives and applications of those, and then multiple integrals, including all the different coordinate systems. And now we enter the third and final part, that's broadly referred to as vector calculus, where we make use of everything that has been covered up to this point. So there's still going to be a lot of evaluation of integrals, but with certain applications in mind and certain theorems that help you to evaluate some of these integrals over curves and surfaces and so on. So a lot of what you saw in pretty much everything that you dealt with in Cal 3 except for series, all the vector stuff, polar coordinates, parametric equations, we're going to need all of that. But we're going to ease into it. Okay.
Does test 2 involve 15.1?
No. So test 2, all right, I know it's going to cause pretty much all of you to tune me out today. But this section's not on the test. I can ask something about it on the final, though. Okay. So we have a first homework assignment that is due after the test. Oh. Because really the purpose of this section is to define a lot of things that you're going to need. So in fact, to cause even those of you who have not yet tuned me out, let me finish that off. There's not a homework on this section either. But it doesn't mean it's not important. I wouldn't get up here and do that just to waste my own time as well as yours. This is meant to set up everything so you'll understand what's happening in the later sections. But one thing I found, and since I have time, I can take a time to briefly step on my soapbox about this. I found this just as a general comment that students tend to be overly short-sighted when it comes to how they handle assignments and so forth. For example, there are some classes in this department, and I'm sure in other departments, where the instructor assigns homework but does not collect it. And what happens, predictably, nobody does it, even though that would do a great job of preparing them for the test. And also, if they do it as it's assigned, rather than waiting until a few days before the test, they would actually understand what's going on in class a bit better. Or in a class such as this one, where there's online homework. I know a lot of the problems have even the handy view and example thing, which is a nice resource to have in case you're having trouble. And if used wisely, it really is a great resource to help you learn the material. But if you use it in the wrong way, and what I mean by that is you see how the example's done. Maybe it's a very similar problem except for some numbers have changed, and you see what's done to the numbers so that you can get the answer to a real problem. Do you really think it's going to help you on a test? Like in last time I taught differential equations, I assigned homework from a textbook, and I collected it, and I graded it. And what did students do? They go online to Chegg and copy down solutions. Do you really think it's going to help you for a test? I found that, again, as a whole, there are always exceptions, but students in general need to be a lot better about thinking about the consequences of how they go about things now when it comes to things such as tests, finals, and so forth. And that taking at path of least resistance is not always a good idea. And you probably are tuning me out already because of what I said about this section. But really, if you're going to tune into me for anything, I hope you tuned in for that. Okay. So now that I've ensured that that sermon will be immortalized on YouTube, I can tell you about vector fields. So what is a vector field? If you have some function that takes in the same number of inputs and outputs. And we're interested in the case where n is greater than 1. So the f is, and I'll use the vector to indicate that so it maps a vector to another vector. All right, so any function that does this, when I use the term vector field, that's what I'm referring to. And in this chapter, in chapter 15, we're going to be dealing with vector fields a lot, so it's important to get used to the terminology, notation, etc. Now, I want to emphasize, in contrast to another term that I've used before, is not exactly the same as what I've referred to as a vector valued function. So to help you see the distinction, a vector valued function goes from, takes in, n inputs, m outputs, and the number of outputs has to be greater than 1. So in other words, your output is a vector, but the number of inputs does not have to be the same. So an example of a vector valued function might be having only a single input, t. And the output happens to be a vector that depends on t. So in this case, cosine t, sine t, and t. This is one of my favorite examples of a vector valued function that depends on only one parameter, just because of the graph. Because if you have a function that returns a point cosine t, sine t, and we only look at the xy plane, because here we have x, y, and z components. So if we ignore the t for now, so what happens if I have, okay, so x is cosine t, y equals sine t. If I were to plot this, like I start with t equals 0, and I let t increase, what am I going to get? What curve will this trace out? Where have we seen things like that before?
Are you just asking the graph?
Yeah, what's the graph? Yeah.
Oh, it starts at the origin and goes to pi over 2, then to negative pi over 2.
Well, so it doesn't start at the origin, because, okay, let's assume that t equals 0. You can think of this as a review of something that, from Cal 3, dealing with parametric curves, and we're going to need that in this chapter. The t equals 0, what point are you going to be at?
0 for y, and then 1 at
Yeah, so 1, 0, you start here. Okay.
traverse.
Yeah, so it's going to traverse what kind of curve? Take a step. Yes, it's a circle. And because of how angles work, theta equals, or t equals 0 is here, and then when t is equal to 45 degrees or pi over 4, you're here. So it's going to trace out the circle. Oops, that was not a good circle as usual. Counterclockwise. Orientation is going to be important. With curves, we're generally interested in this kind of counterclockwise orientation. So I'll even fill in the arrow to indicate which way the curve is being traversed. Once you get to t equals 2 pi, you're just going to keep traversing that circle over and over again. Whereas if I wanted, so this is counterclockwise. If I wanted clockwise, it wouldn't be hard to get. For instance, if I were to do x is sine and y is cosine, then that would have me starting up here and traversing the same circle, only clockwise. Okay. I hope we're not dealing with that now. But that's only for the x and y. but ignoring the z component. But now let's bring that back in. So now we're in three-dimensional space, and we know how x and y are going to behave. So we're starting here at the point 1, 0, 0. So if you look down on this, this is going to be tracing a circle. But how is the t going to impact this? Now we have a curve in three-dimensional space.
More of a spiral.
Yes, it's going to be a spiral, like a helix. So it's going to keep looping around the z-axis, but increasing in height. So often it can be a good idea to first focus on x and y, because that's easier to visualize. How's it behaving in that case? And then include the z to, like once you understand the behavior over here, now throw in the z component to get the rest of the picture, literally. Okay. So that's a vector-valued function, and we will be making use of those in this chapter. And it's also worth pointing out, even though this might seem like a less significant section, a lot of times students try to get through problems not really understanding the very terms that are being used. And today is about defining certain terms of importance. So that could be because they're going to come up later. Okay, so a vector field can be written in different ways that are some more compact than others. So I have x represents a point in n-dimensional space, and the output f of x is also in n-dimensional space. So I can define each of the components of this vector f of x, the f1, f2, all the way to fn. So each component of f of x is a function of these same n variables, and these are called component functions. Because for each x, you plug in a specific x, you're going to get a vector of n components, so that's why we call these component functions. All right. Okay. Now, here I'm defining this for a general n, but pretty much any example we're going to be dealing with in this chapter is going to be n equals 2 or n equals 3. Okay. Now, in this chapter, compared to previous ones, we're going to get a bit more into applications and assign vector fields that we deal with certain meanings. So I'm going to give a couple examples of interpretations of vector fields, and I'm not going to just bring them up now and forget about them. We're going to need them later. Okay. So examples of vector fields. Okay. So a vector field, and I'll stick with 3 dimensions, v of x, y, z. It's called a velocity field. For a fluid. What that means is, at each point, x, y, z, the value of this vector field, v of x, y, z, gives the velocity vector of a fluid. Because if you think of a fluid as being a collection of, for instance, molecules, if a molecule that's located at x, y, z is traveling in a direction indicated by v of x, y, z. Okay. Now, the magnitude, which I use a double bars to indicate, although you might be more familiar with seeing just plain old absolute value used instead. So this is a magnitude of v of x, y, z. So that would be the sum of squares of using the same notation as over there, v1 squared plus v2 squared plus v3 squared, the three component functions of v. That indicates the speed of a fluid at that particular point. Okay. Now, so one property that a velocity field would have is this. If you have a curve, like the curve from this helix example, a curve C of t is called a streamline, also known as a flow line, of a fluid in question if it satisfies this, that at any particular time, C prime of t, which is a vector, this is the tangent vector, something else we'll be dealing with quite often in this chapter, is given by the velocity field at that point. So given a velocity field v, if you were to solve this differential equation, for instance, then that would you could like plot the curve C of t, and that would, if you do this for to plot several streamlines, then that gives you a visualization of which direction the fluid is moving in. Okay.
And what did you say? C indicated. Okay, never mind.
Yeah. So tangent vector that indicates velocity. C of t itself indicates position at time t. Okay. And what you can do is to get an approximate streamline. If you plug in an initial, if you have an initial point, so you might be given some initial condition, and this would make the most sense to someone who is taking differential equations. But the point is, this is something that would be like given information. So you're starting at this point, and the question is now, where does this particle of fluid move from here? So x1 would approximately be equal, so the next point would approximately equal your previous point plus the change in time times the velocity. And that would just be given by taking your initial point and plugging it into your velocity field. So, in other words, the change in position divided by the change in time is the velocity. And you know that formula already. So that's really all I'm using here. And then you can keep going. X2 be x1 plus the change in time times the velocity at this new point. And you can keep going and then trace out an approximate streamline. The more often you sample in time, the more accurate your streamline will be. Okay, so if you have a velocity field, you can use that in conjunction with a given initial point to see which way the fluid is going. So, for example, if I were to try to draw this, here's your initial point. So you plug this point into your velocity field. Let's say it gives you a vector going in this direction. So then you multiply. So this would be v of x naught. Okay. This vector here, and then you multiply that by the change in time. So that might take you a little further, and this gives you x1. And then you plug that in there to get another vector, v of x1, and then you multiply this by the change in time again. So this gives you x2, and so on, and you just see where it goes from there. Now, there are a lot of applications where you're simulating fluid flow. For instance, in my former life when I was in the petroleum engineering department at Stanford, our simulations of oil recovery would involve computing streamlines, because what's happening in that kind of application is you're injecting gas into oil well, and you want to follow its streamlines to see where is it going to come out at a production well, and how long will it take. And oil company management is very interested in that, because they want to know how much oil they can expect to recover and how long it'll take to recover it. Okay. Now, so this is one example of a vector field. Also, simulation of fluid flow like this is also like a totally different application of it is in animation. So all the computer graphics that you see in movies these days are solving some sort of differential equation to understand the movement of a fluid over time, or interactions between fluids, like to effectively simulate fire. And how it interacts with the air. Okay. Go ahead and do attendance. Okay. Another example would be I'll define Alpha notation in a moment. Actually, can anyone guess what this is referring to? Just by the constants involved. What? Sorry, what?
Gravity.
Yes, gravity. So what we have is, so we have two objects of mass little m and big M. And we have R. Okay. So we assume, for like, think of R as a position vector, so we're assuming that this mass is located at the origin. So then the vector between these two, R, would indicate the position vector of a mass little m in that coordinate system. So capital G is the gravitational constant. Okay. Now, so what this indicates is the gravitational force exerted on, and I'll just abbreviate by that the larger object that is located at the origin is exerting on the smaller object of mass little m. So this is called a gravitational field. Now you may remember learning that the gravitational force is proportional to 1 over the distance squared between the objects. So it might seem strange that I put distance cubed down below. But keep in mind, this R has a magnitude also. So if we look at the magnitude of this, the magnitude of this would cancel with one of the factors down here. So in the end, you'd have, so the magnitude of this gravitational force, because this has magnitude and direction. would be little m, big M, G, magnitude of R divided by magnitude of R cubed, which would then simplify to what you'd expect, that's proportional to 1 over the distance between the objects squared. Okay. And there's a very similar kind of vector field indicating the electrical charge exerted by so the electrical force exerted by a charge at a particular point. So we would just same kind of formula, just the constants would have different meaning. Okay. All right. Now, one aspect of vector fields that's going to be particularly important to us in upcoming sections is this: a vector field, big F, is said to be conservative, also referred to as irrotational, if F happens to be the gradient of some scalar valued function little f. So if I were to write this, now this is a vector equation because it has 2 or 3 components. But if I were to write out what this equation means component by component, we have the first component function, f1, is partial of f with respect to x. Big F2 is partial of f with respect to y. Big F3 is partial of f with respect to z. So one thing we'll learn to do in a couple of sections is, given big F, can we, is this a gradient of some function little f? There's actually a remarkably simple test to determine if that's even possible. Given that it is possible, can we recover a function little f? And there's a procedure for that. Those of you who have taken or are taking DE 285 would actually recognize this as similar to what you would do for solving exact equations. And in fact, how you check is basically the same procedure, but in that class you only do it in 2 dimensions. Here we're going to do it in 3 as well. Okay, and little f is called a potential function. And another term for big F, we can call it a conservative vector field or irrotational vector field, also known as a gradient field, just because it is a gradient of some function. Okay. Now, I'm going to give a couple of examples of 2-dimensional vector fields, one that is conservative and one that's not. And so you can see the difference in how they look, and that will also suggest why we could call it irrotational. So even though the vector fields themselves will seem to be very similar in terms of the formula, their behavior will be quite different. So first example, I will let f of x, y, so 2-dimensional vector field, equal minus y and x. And then for my second example, almost exactly the same, just plus y and x. Now, what I can do is to visualize this vector field. And it's a very tedious process, and that's why I generated the figures in the notes in MATLAB. I can pick a point, x, y, so in this case 1, 1, and I'll plug that into the vector field, see what vector I get, and then draw that starting at this point as an arrow. So here's my point 1, 1, and I plug it into here and I get minus 1, 1. So starting from here, I'm going to go in that direction indicated by that vector, minus 1, 1. So I need to go 1 to the left and 1 up. So it's going to look like that. So this is, so at the point 1, 1, here I have V, or not V, F of 1, 1. Now, that doesn't really tell us anything, but if we do more points, we can see how it's going to go. So for instance, at this point, 1, 0, my vector is going to be 0, 1. So I'll fill that in. Here I have x is 0, y is 2. So if I plug that in here, I'm going to have minus 2, 0. So that'll put me over here. Now here I have x is equal to minus 2 and y is 2. So that's going to give me, I take the y component and negate it. So minus 2, and then I just take the x component as is. So I get minus 2, minus 2. And that'll put me down here. So my next point, I'm at x is minus 4, y is 0. So I get the y component negated, that's a 0. And then minus 4. So what do you think is going to happen if I continue? If I were to keep plugging points into F and keep drawing the path, what's going to happen? Yeah, it's going to keep spiraling outward. And I have a picture. So in the now these are not exact streamlines, but what we have is this picture in the notes, page 106, that it keeps swirling around. This is the opposite of an irrotational vector field. It's highly rotational. So this is not conservative. It's not a gradient of any function. And you can't tell that from a formula, but in a couple sections I will show you how to do that. Okay. Now, for the other example, okay, where we just have yx. So when x is 1 and y is 0, I'm just going to have 0, 1. When x is 1, 1, that'll go in this direction. If x is 2, 2, if x is 0, 0, you get nothing. 1, 0, you get 0, 1. Okay, when x is 1 and y is minus 1, so from here I'm going to go back this way and up. So if you were to keep plotting points, what you'd find is it has a way of resisting rotation. Okay, not sure where my picture went.
I'm not quite understanding how you're making it do that.
All I'm doing is, so each point, plug that in here, then draw that vector. So like if I were to do, for instance, x is minus 1 and y is 0, this calls for switching the components. So f of minus 1, 0 would be 0, minus 1. So it's going to, so from this point, minus 1, 0, I'll draw that vector. Then f of minus 1, minus 1, swapping components gives you the same thing.
Okay, I see what you mean.
Yeah. Okay, if x is minus 1 and y is 1, then wait. Okay, x is minus 1, so we go. Okay. All right. So now I have a picture of a whole vector field, page 107, and what happens is, if I were to draw like curves that describe the behavior, it goes something like this. And I've captured a little of that here, but it would take more points to really see it. So on these figures, I plot a bunch of points. So whereas here you would see just circles, concentric circles for your streamlines. Here it's the opposite of that. There's no tendency to swirl around anything anywhere in the xy plane. And in fact, it's a gradient of f, where f of xy is equal to x times y, because if you differentiate with respect to x, you get y. If you differentiate with respect to y, you get x. But the same cannot be said of the previous example. There's no way to find a function f of xy where you take derivative with respect to x, you get minus y, and with respect to y, you get plus x. So visually, there's a difference between a heavily rotational and a completely irrotational vector field. So a couple sections will be dealing with these a lot more. So all the terminology I've introduced today, something's going to keep coming up. So it's important that you get used to that now. So any questions about these kind of vector fields? So notation-wise, if I have something like this using little f of x, y, z, where there's no vector symbol up here, that is a scalar valued function. So the output is just a number, like some number w. Whereas if I tend to use lowercase letters for these. If I use an uppercase letter and I put a vector sign on top, and in the notes in most books, it's actually in boldface. This is how I refer to a vector field. So we're going to be doing a lot of operations, the course of evaluating integrals and such, that work with either scalar valued or vector valued functions. So it's very important to keep track. What kind of object is this? Is it a number? Is it a vector? If you perform operations on it, what do you get? Dot product of vectors gives you a number. Cross product of vectors gives you another vector, and so on. Because if you can't keep track of those kind of things, then how do you expect to do problems? So, yeah.
How come when you get to -1, like you got, how come it's not just stopping?
Okay. Wait about stopping though, like, well,
Because you said you put it back in and you swap around, it's going to end up being the same thing over and over.
right, but then you draw it from here, starting from a point you plug
Or
in.
you just keep doing -1.
Yeah, like if I want to know what how a vector is behaving at the point, let's say 10, 10, way out here, I'll plug that into here, and 10, 10 is my starting point, and the vector field indicates you have a direction in which you go from there.
Oh, okay. It's
Yeah.
not just that point on the.
Right, yeah. Okay. Okay. Does anyone have any homework questions or practice test questions? We have a little time for that. I think of the next homework due on the 30th. I figured nobody would be doing homework on Halloween night.
Is that Monday?
Yeah, yes. What?
Don't tempt me. The
Okay.
30th is actually Sunday.
The 30th is Saturday.
Um,
I'll be good.
okay, I know some people started it, not very many, but so. No questions at all? Anticipation of a test coming up in a week.
Yeah, I'm screwed.
What?
I'm screwed.
Okay, if you say so. You still have plenty of time to do something about that, though. Okay. You guys want to get out here early. Okay, fine.
I can't go to work. That's it. You're waiting for the next